Hi, Francis, Julie.
How's
So Kaltura, when I tested it earlier today, my computer just rebooted. I think it was just, even during the last times it was recording, it was taking up too much memory. So I'm just wondering, the DSP captioner, I'm just wondering if it would work if we give you the Zoom recordings with the MP4 files for captioning. Okay, they are not responding at the moment. And I'm wondering if it's just me, if it's just us, or others have also been facing Kaltura issues.
I know it was down end of last week through the weekend, but I don't know if it's back up / fixed by now.
Right, because I mean, my point is if the Zoom captioning works well, and it also looks like the only issue was with regards to. Okay, so I got a message saying you can email dsp-captioning@berkeley.edu for help with caption media. So Julie, could you just follow up with them and just to make sure we're okay?
Yeah,
right.
I can definitely do that. I'll make sure that they got the last 2 lectures too.
Okay. Because if Zoom is working fine, I would just like to stick to that, and it makes our life simpler. Right, I'm happy to take any questions. We still have 5 minutes to go. I'm going to try and do a Zoom poll today. We'll see how that goes. All right, wow, people are trickling in.
Hey Karthik, it won't let me assign captions to the DSP person. Does it show up for you?
It won't let you. Okay, closed caption, assign a participant to type, and then DSP.
Thank you. Yeah,
right.
I think it won't let me do it if you show up first. Like the first host gets the option.
Okay. So as long as you remember and remind me to do it, I'll do it. Okay.
Mm-hmm. Thank you.
This is actually kind of this is just a more general question, but for the discussion sections that weren't there yesterday, when are the makeups again?
So you guys can join my discussion sections, and that's tomorrow at 3 or Thursday at noon. And then I think Francis, your office hours?
Yeah, I have 11 to noon tomorrow. So in case you can't make any of those two, we can do the section problem there as well.
Okay, thank you.
And if for some reason, that still, it leaves certain gaps, just email me and we'll try to figure something out.
Yeah, I also have office hours 5 to 6 after class today and 5 to 6 tomorrow. So if that works for like some people, I can also make a breakout room and you guys could do the section problem there too. Happy to accommodate that as well.
All right, so that's the hour. Let's get started. So I just want to make a few announcements. You would have received my email on my new office hour times starting next week, which will be Monday 12 to 1 and Friday 11 to 12. And there's also a new link. You should let us know if the homework groups that we've created are not working for you. It's one thing if you don't want to participate in them, that's entirely your choice. But if for some reason you're feeling isolated in being able to work through homework problems, just email us and we'll see what we can do. The other thing that I sort of want to emphasize is that although you have a textbook, and I'm trying to stick to that as much as I can, I'm not following the script exactly. And that's for a couple of reasons. And that's because, you know, I feel like sort of my goal is to convey conceptual things as efficiently as I can. And for a number of reasons, I don't find the way it's presented in the text to be as efficient. There's a lot of repetition, so I try to avoid that. And so for the large part, if you follow the notes, I think you should be good to deal with both the homework and also the exams. And there are specific areas where after you read the homework, something is not clear. That would be a good place to go back into the text. Of course, you know, if you have lots of time in your hands, feel free to go read the text in as much detail as you want. And as always, you know, just feel free to write to me if something is not working, something I can do better. I'm happy to hear your thoughts. All right, so I want to begin by doing a quick recap of enzyme kinetics, which we began the last time, and then we will get started onto the classic chemical engineering part of this class, which is chemical reactor design. So we reviewed and we worked through the canonical example of enzyme kinetics, which is the Michaelis and Menton model, where you have a substrate that's binding to an enzyme in a reversible fashion that creates a reactive intermediate that ultimately, with some rate, releases the product that one is interested in and also frees up the enzyme. And in sort of these problems, and you also have a homework problem, what you will have to recognize is that you have a certain total amount of enzyme, which is the initial amount of enzyme that you add, and you also have a total substrate. So in that sense, this is a closed system. I think there was a question on Piazza. And your goal is to identify what the kinetics of product formation is as a function of the substrate concentration. That's the idea. And the way we did that was to write down the balance for the reactive intermediate. And we applied a pseudo steady state hypothesis that allows us to calculate the reactive intermediate concentration, that is ES, as a function of the enzyme and the substrate concentrations. And ultimately, what we are interested in is the rate of formation of the product, which is this over here, which is exactly equal to the negative of the rate of the consumption of the substrate. And what we found is that in the Michaelis-Menten model, it has this interesting form, which has the substrate in both the numerator and the denominator. And if you plot the Michaelis-Menten sort of RP, which is dP by dt as a function of substrate concentration, you see this saturation type of behavior, where I mentioned earlier that at the very extreme, you have what's called the enzyme limited regime, where you have a certain maximum rate at which you can form products, and you can't go beyond that, even if you increase the substrate concentration, because there's only so much enzyme. And then at low enzyme concentrations, I mentioned there's a linear regime, and I think Francis pointed out in the chats that this is appropriately called substrate limited. All right, and then we have these two parameters for the Michaelis-Menten system. We have a Vmax, which is the maximum rate at which you can form product. That's simply the product of the, so the y-axis here is dP by dt. It's exactly the same as last time, and then I'm calling it RP. Okay. All right, so we have these two parameters, Vmax and Km. Km has units of concentration, which is we call the Menten constant. So the question now is, what happens to this curve if you are varying Km or Vmax? So first question is, what will happen if I vary Vmax? Any idea? Thoughts?
Well, the slope would get either lower or higher in the substrate limited regime, depending on whether, actually, no, the upper bound would increase or decrease depending on whether Vmax was increased or decreased.
So what you will see something is like as follows. You will see this or this or this. So the maximum, so this is increasing Vmax. So increasing Vmax, right? And so the maximum rate of product formation increases, and there's a simple interpretation. There are two ways in which you can increase Vmax. One is to increase K2, which is the rate at which the transition state complex is formed into product, or you increase the total enzyme. And both of these would have this effect where the maximum achievable rate of product formation will increase. What about Km? And if you remember the last time, and there was some confusion, what I said was, so this is Km. I said low Km means a fast enzyme, and high Km means a slow enzyme. Does anybody want to volunteer to tell me what would happen if I change Km?
So if Km is bigger, that means that it takes more amount of substance to get to Vmax.
Correct. So if you regard this as the typical curve, what you will find is that as you increase Km, you will see something like this. And as you decrease Km, you're going to see something like this. So this is increasing Km. And so at high Km, you will still achieve the maximum rate corresponding to Vmax. So Vmax is going to be the same, but you need a higher substrate concentration to get there. And that's the interpretation between fast and slow. So typically, biochemists would like to characterize enzymes based on their Kms, And the reason is they want to figure out how much enzyme you need to add to achieve a certain conversion of substrate. So for a lot of enzymes, they would be interested in what the Km is. Okay, so in this case, we derived an expression for the rate of product formation using the pseudo steady state approximation. I just want to go through the drill of what if you assume the quasi-equilibrium approximation. And so the quasi-equilibrium approximation here would say that this reaction is at equilibrium. And what does that imply? That implies that the forward rate of this reaction is equal to the backward rate. And the way I can write that is that ES over ES, E times S over ES, is essentially K sub minus 1 over K1. That's the equilibrium constant for this reaction. Does everybody agree to that? Is that clear? I'm just equating the forward rate and the backward rate and rearranging the terms.
Yeah.
Was that a question? Yes, no?
Oh, no, it looks good.
All right. So I can calculate the value of the concentration of the intermediate that I'm going to call star as essentially S times E, sorry, and I am going to call this particular ratio as KD, where again this has units of concentration, as you will see, and this is the D stands for dissociation. So if you will notice, all this reaction is telling you, this reversible reaction is describing a dissociation process, and so I'm going to call it KD. And so this essentially is 1 over KD. Now I can apply the condition, the site balance for E, and so the free enzyme over here is essentially the total enzyme minus ES, and I can substitute that and solve for the concentration of the intermediate, and what I'm going to get is that the concentration of the intermediate in this regime is ET S over KD plus S. And so this is what I'm going to call the QE, the quasi-equilibrium regime. Right. And so again, here I can compute the rate of product formation, which is all that I care about, which is dP over dt. And again, this is the same as minus Rs, which is the rate of substrate consumption. And that is going to be K2 ET S over KD plus S. Now notice what has happened here. This is interesting. So the rate of product formation in the case of the quasi-equilibrium assumption has the same functional form as in the case of the pseudo steady state approximation. Okay? And here too, in this case, I have essentially the same Vmax, but instead of the Menton constant, I have KD. So instead of Km in the pseudo steady state approximation. So the same functional form. So same functional form. And so what that basically means is that if I plot the substrate concentration or the rate of product formation, I'm going to get essentially the same thing with Vmax, except that in this scenario, the half maximum velocity will happen when S equal to KD. And so one can ask, when is QE valid? And that basically means that you want Km to approximately equal Kd. And again, if you substitute the values, you will notice that you want is approximately equal to K minus 1 over 1. And this is true if K2 is much lesser than K minus 1. And so what that basically means is that this reaction is slow and this reaction is fast. It's their relative rates that matters. Okay? And so that's when the quasi-equilibrium approximation is valid, when one of these reactions on the other side of the reversible reaction is much slower. Okay, is that clear? Any questions? All right. So let's suppose you're in a biochemistry lab and you've been asked to measure these constant for enzymes. And you've been given an enzyme and you've been asked, I want to know what's the Vmax and what's the Km or the Kd. And of course, you know, it has to be one of them. So typically the way these experiments would be done is the following. What you would do is you would create multiple reactions. And in each of these reactions, you would seed different concentrations of the substrate of interest. And the substrate would have some, let's say, some magenta color that you can probably visualize using some sort of a spectrophotometer or some other instrument. And so here you have a low concentration. So essentially, this is increasing concentration of S. And then what you would do essentially is you would load on each of these at some time a certain concentration of the enzyme, which let's say you've obtained from a company like Thermo Fisher or some other, or you purified it using some process. And then what you would do typically, or what was done by Michaelis and Menton, is once you add this enzyme, you've activated the reaction. And so you're going to start converting the substrate into product. What you would do is you would typically wait for a certain amount of time, let's say, I don't know, 3 minutes. And you would measure the amount of color that is changed, which is your proxy or readout for how much substrate has been consumed in those 3 minutes or how much product has been formed. And then you would divide that by 3 minutes to calculate the rate. So essentially what you would do is for a variety of substrate concentrations, you would calculate RP. And so you have this data. What are you going to do? How are you going to estimate Km and Vmax? All the samples would have the same ET in this experiment, correct? Otherwise, you will have different Vmaxes. Plot the logs. Okay. So I plot the logs. Let's say I plot log of RP versus log of S, and I think you would see something similar. How does that help you? Any other takers?
Could you use the two regimes? So like the one at the beginning, because that's a linear regime in the enzyme to get Vmax, and then use the upper regime, or yeah, you can use a limit to get Vmax, and then you can use the linear regime to get KD or KM.
Okay, so what you're saying is I take this value over here.
I can't see what
And-
you're pointing at. Oh, yeah.
Yeah, I take this value and then I know ET, so I can calculate K2, right? That's fair. But typically, one would like to use the whole data set to do an estimation, because that way you're buffering yourself against specific errors. And so I would say plotting the log could be helpful in many instances, but in this instance, it's not going to help you because the functional form is not an exponential. So you're not buying anything. Like in the Arrhenius equation, there was an exponential there. So plotting it as a log of something converts it to a linear function. But that's not the case here. But the idea, so of course, in today's world, you can just use MATLAB to probably put this in and it'll do nonlinear fitting. But before the days of MATLAB, in the days of Michaelis and Menten, one thing people could do is they could fit straight lines. They could estimate the slope and the intercept. So the idea was to convert the Michaelis-Menten equation, which is R sub P equals Vmax S over Km plus S, which is now the same as minus R sub S. So I'm going to use these two equivalently, okay? And the idea is, so this is let's say minus R sub S or R sub S. And so the idea was to convert this to a linear form. And one way you can do that, if you see, is if I now take the inverse, what you will see is that now minus 1 by R sub S is essentially 1 over Vmax plus K sub M over Vmax over 1 over S. And so you can imagine that this is like Y, this is like X, and this is the slope, and this is the intercept. So the idea here is that I can plot now 1 over S in the x-axis minus 1 over RS in the y-axis, and maybe I will see something akin to a straight line if my Michaelis-Menten model is correct. And then I can fit a line through it where the slope will be Km over Vmax. And in this case, this will be the intercept, 1 over Vmax. And this is called, it has a name, it's called a Lineweaver-Burke plot. Again, I don't know the history of this. And it could be Lineweaver and Burke who discovered this together, or it could be Lineweaver-Burke. Okay, so that's how you would do it. Question, does anybody see a problem with this? Something would go wrong?
What happens if Vmax is 0?
If Vmax is 0, the only way it can happen in the Michaelis-Menten model is if K2 is 0 or you've added no enzyme.
Oh, okay.
And so in both those situations, you probably shouldn't be doing the experiment, right? And so that's the only way. And of course, if Vmax is 0, you would expect essentially 1 by RS to be 0. And so you'll have only points in infinity. You will not see a straight line.
More than that, in your original data, Vmax is 0. Wouldn't you just have zeros because Vmax is in the numerator? There's only one term in the numerator.
Correct. So you will have only 0. So your rate of product formation or rate of substrate consumption would be 0 identically. So 1 over RS essentially would be infinity. So there would be nothing to measure. So let's assume that Vmax is non-zero. So any idea what could go wrong here?
As your substrate approaches 0, you'll have some problems too.
Yes. What kind of problems?
The values will start getting really, really big.
Right. So your point is, and this is excellent observation, which is that in general, it's easier to measure large quantities than small quantities. The moment you have, all right, thank you for that piece of general knowledge, Francis. It's in general, would you agree that it would be harder to measure things that are small than things that are big, right? Because you have lower quantities. So what would happen is, because you are measuring or you're plotting 1 over S, let's say this is the true line, but because of these measurement errors, you will have these large swings over here. And so you could have large errors. So this could be the true line, but because of these measurement errors because of 1 over S, you may misestimate as something like this. So in general, plotting the reciprocal of something has the danger that you will be misestimating the true behavior because of errors. And so as a consequence, there's another way to plot this. So this is strategy 2. So this is strategy 1. So strategy 2 is what's called in Fogler a Haynes-Wolff plot. And there the idea is simply multiply this equation by the substrate concentration. So what you get when you do that, and again I'm just rewriting it, is that you get S over Rs equals Km over Vmax plus 1 over Vmax times the concentration of S. And so here, what you would be doing in Haynes-Wolff is you would be plotting S as, and on the y-axis, you will be plotting S over Rs. And here too, you will hopefully get a straight line if the Michaelis-Menten kinetics is correct, except that your intercept would be Km over Vmax. And what would be the slope? What would be the slope?
1 over Vmax.
1 over Vmax. And there is, I believe, in Fogler something called, ED and Hofstee plots. I have no idea what it is, but you can go and take a look. Okay, these are multiple different ways to plot a straight line.
I had a question about when you have the error from the first plot that you put.
Yeah.
If you do have that error, does the method of regression ever have any effect on how much that error actually matters?
It will propagate, right? It will propagate through your regression line. So when you do regression, you're trying to fit the best straight line that minimizes the errors of your observations. Mm-hmm. So, but if your observations have error, which is what is in this case, your line, the best fitting line, would try to sort of capture that. And so as a consequence, your final estimate would have errors.
And you're assuming that these errors aren't like extreme outliers, right? They're like within some sort of like standard deviation from.
Yes,
the
true.
true line.
I think what I'm assuming is that in general, if you have small quantities that you want to measure, the errors as a fold change of those small quantities would be larger, right? For instance, if you're measuring, a quantity that has value 20, you might measure 18 or 22, and the fractional error would be, let's say, 5% or 10%. But if you're measuring something that is 0.0001, and ultimately all measuring instruments have issues, you could be measuring something instead of 0.0001, you could be measuring 0.0005, which in relative terms, absolute terms is small, but in relative terms indicates an error of 500%.
Yeah.
And if you take the ratio or the reciprocal of that, you're going to see these large swings over here.
That makes sense.
That makes sense? All right.
Yeah.
Okay, so if we have no questions, let's start thinking of going beyond kinetics to design chemical reactors. So let me do a quick recap of stoichiometry. So I have my generic reaction, generic irreversible reaction, A moles of A with B moles of B gives me C moles of C with D moles of D. And I've defined my R sub J as moles of J formed divided by time and volume. And J here can be A, B, C, or D. And so I've also defined my stoichiometric coefficients nu sub A equal to minus A, nu sub B equal to minus B, nu sub C equal to C, and nu sub D equal to D by convention. And I have my equation, which is always the case, RA over nu sub A equal to RB over nu sub B equal to RC over nu sub C equal to RD over nu sub D. And so this is from stoichiometry. And so what that means essentially is if I'm given any one of these, which is, let's say, RA equal to K CA to the power alpha, CB to the power beta, or it could be minus RA K1 CA by 1 plus K2 CB squared. I'm just making things up. If I'm given any of these, I can calculate the others. That's the idea. All right. So let me just leave the space over here a little bit, and let me begin by thinking about chemical reactors. So chemical reactors are entities where one or more chemical transformations take place. And so we have, let's say, typical industrial reactors that manufacture polymers and other things. Any other examples of chemical reactors that are, let's say, more mundane?
A beaker.
Yeah, you can have a beaker in a lab. Anything else? Ovens, correct. So one of your TAs loves baking bread. So the oven is a chemical reactor. In fact, the loaf of bread itself is a chemical reactor. Stomach, fantastic. The sun, and even your body is a chemical reactor. Okay. So what we are going to do right now is to do something called, we're going to begin with the design of reactors. That is, you want to design reactors that carry out these transformations effectively. So they have to depend on your kinetics. And we're going to deal with isothermal. So the first part of this class, or the next few lectures, we're going to deal with isothermal reactor design. And that means my T is a constant. And then after the first midterm, or shortly after the first midterm, we will go to non-isothermal designs where your temperature can vary. You have to deal with exothermic or endothermic reactions. In the initial phase, we will make some ideal assumptions that that things are well mixed. Your reactants don't need to find each other. But then at some point, we will try to introduce the effects of transport. And this is especially important in catalysis, where the reactants have to adsorb on the surface of catalysts. And towards the end of the course, we will also try to think of non-ideal reactors which may not be well mixed. So you have to take into account the hydrodynamics, which is the mixing of these fluids and these have an impact on the conversion. And so you can think of these as chemical kinetics in open systems. And the first part of the course was to just deal with chemical kinetics in closed systems. All right, so the first thing we want to do is to do a mole balance in a chemical reactor. And this is in some ways fundamental because this is where you would begin all your analysis of applying kinetics to a reactor setting. Now, there are many types of reactors. And these come in various shapes and sizes. They come with bells and whistles, with various control systems, with ways in which you can heat up the fluid, you can cool the fluid. But to begin with, we will consider something as very general, as possible. Which means we will abstract away from the finer details, which won't matter. And this is, again, an important skill you need to have as an engineer. You need to forget about details that don't matter and only focus on the very basic things. So that's what we will do. So let's assume that we have, this is our reactor. And so it's some potato-shaped reactor. And every reactor, since it's an open system, has to have an inlet. And we're going to think of an inlet. So this is in and an outlet. Now, of course, when you flow things in and things are reacting, you might have species A, B, C, D. I'm just going to consider the perspective of one species at a time. So I'm going to think of species J. So mole balance. So we can think of this as balance for species J. And so the quantity of interest is the molar flow rate of species J, and I'm going to denote it as F sub J naught, which has units of moles of J per time. And at the outlet, you will have F sub J, which again is moles of J over time. So just how many moles per unit time is entering and leaving, and they would be different because you have something happening inside that's either consuming J or producing J. Okay? And so let me write down what we're going to consider is an isothermal ideal reactor. And so we will try to assume that temperature and pressure, if relevant, are the same everywhere in the reactor and correspond to the feed conditions. That is Fj naught. So whatever the temperature and pressure of this inlet is going to be what is going to be the temperature and pressure conditions of the reactor. This is for only temperature and pressure. So let's do a balance for J. So balance for J. And so the input of J minus the output, right, plus the production of J by the reaction. And again, I'm not going to consider consumption because that's just another form of production depending on the sign. So the input minus output plus production equal to what? What should it be?
Accumulation.
Accumulation. That's the most basic form of the mole balance. And so if I have to write this for J, I have Fj naught minus Fj plus I'm going to call this Gj. And for the accumulation, I'm going to write this as d by dt of Nj, where Nj is the number of moles of J in the reactor. Okay, so at any given point of time, there will be some Nj moles, which is a function of time, and that's in the reactor. Now, how do I write Gj? I can imagine that the reactor is divided into these little volumes because there is spatial variation. I can think of this as delta V1, delta V2, and some delta Vk, and there are many, many such infinitesimal volumes. Now, the rate of generation of J in one of these is going to be R sub J as a function of delta V1, and this is going to be over here R sub J as a function of delta V2, and the brackets delta V1 delta V2 just says that depending on the concentration of J, which can be different in different parts of the reactor, I'll have different generation rates. Okay, is that clear? And so the way I can write Gj, which is the total rate of production, is simply a sum from k equal to 1 to n, where n is a very large number. So we're assuming that the reactor is well mixed, but we'll get to that. So at the moment, I'm not assuming it. Okay? Which is R sub k as a function of delta Vk times delta Vk. And if you take the limit delta Vk tends to 0 and n tending to infinity, you can write this as an integral. Sorry, this should be not R sub k, this should be R sub j as a function of Vk. So it's essentially R sub j integrated over the entire reactor volume. That's Gj. So I can write my general mole balance again as F sub j naught minus F sub j plus integral R sub j dV equal to d and j over dt. And I can do this for all species J. And this is the for all symbol. Okay. And as an aside, I may not have just one reaction. I might have multiple reactions happening. Just like you saw in some of these non-elementary steps where you have multiple reactions happening at the same time. And so an aside is when there are multiple reactions, and I'm going to call reactions, number them as 1, 2, 3 to R reactions. I can define R sub j and m as moles of J, again, moles of species J, formed by reaction M over time volume. And so if I had to substitute in this case an expression for the total rate of production of J, what would that be? when I have multiple reactions.
You could have multiple integrals for each reaction, or like one integral per reaction.
Yes, you can have multiple integrals, but how would I combine them?
You could have a double integral over the number of, so over m and then over j.
I would disagree with that. I don't think you need a double integral.
Could you just sum?
Integrals?
You just need to sum, exactly.
Oh.
So all that it would be is you would be summing from, let's say, m equal to 1 to r sub jm. All of these reactions are happening inside this volume. And you just need to sum them up. And again, we will see this explicitly when we deal with multiple reactions, but this is just an aside. Okay, so now let's get down to business and let's introduce types of reactors. So you have types of reactors. And so the first reactor that we are going to deal with are batch reactors, and we're going to deal with a reactor that's called a batch stirred tank reactor, or a BSTR. And this has certain properties. So this batch reactor has no inlet or outlet. And reactants are usually filled, and the industrial term for this is they're charged. The reactor is charged with the reactants through a hole in the top where a pipe might be connected. And usually these batch reactors are used for small scale operations. And so this would involve, let's say you want to try a new compound, so you want to pilot a new process. They're definitely involved or used to produce expensive goods where you don't have a lot of quantity and you just want to sort of cook them in one go. And so especially for cosmetics. And I bet you've seen batch reactors somewhere. So can you give me some examples of batch reactors?
A fermenter?
Fermenter. So if you've seen these reactors in these craft beer houses, those are batch reactors. So, fermenters.
Would electroplating count as a batch reactor? Like dipping metal into a bath and then having them be plated?
I think so. It would count as a batch reactor because you're not putting in reactors. I'm not an expert in electroplating, so the true answer is I don't know. But from whatever you've described, it would be a batch reactor. Okay, so we're going to have a fancy symbol for a batch reactor, which is essentially one box with a stirrer and no input or output. That's a batch reactor. And so let's do a balance for a BSTR. So BSTR balance. So I always begin with my general balance, which is over here. And I suggest that this is the only thing you need to remember. I think Fogler has about an Avogadro number of ways to write the same thing. And I would sort of encourage you to just focus on the basics. That's at least what I do. I don't have a very good memory for these things. And so Fj naught equal to Fj is 0. That's the assumption, no inlet or outlet. And so what you have in terms of your mole balance equation for species J is dNj over dt is Rj dV. And the other thing I'm going to assume, is perfect mixing in this case. So that's Talia's question. So assume perfect mixing. That means my concentration is uniform. So C sub j or R sub j is uniform, and there is no spatial variation. And in this scenario, I can pull R sub j out of the integral and write this as Rj times V. And so this is my basic batch reactor equation that I'm going to call BSTR1. And since, and it'll become clear why I'm calling it BSTR1. And since I'm dealing with a number of moles per time, I'm going to call this the molar form of the reactor balance. And again, this will be clear why I'm calling this a molar form. And so this is an ODE. And so if I want to solve this, I typically will need to provide R sub j, which is the kinetic rate law. And to solve an ODE, you're going to need an initial condition. And how many initial conditions are you going to need?
Just one.
Just one. It's a first order ODE. So I'll give you something like at t equal to 0, n sub j equal to n sub j 0. And I'll give you obviously the rate law. So in addition, since we're chemical engineers, we like concentrations, you can rewrite this in what I call the concentration form. How do I write the concentration form? So n sub j, which is the total number of moles. So this is the total number of moles of j in the reactor. How will this be related to the concentration of j?
The concentration times the volume.
Correct. Concentration times the volume. And so I can substitute this in BSTR1. So sub in BSTR1, I can write this as d by dt of Cj over V equal to Rj V. I can differentiate this using the chain rule. Again, I've not assumed anything, so I'm going to differentiate. I'm not going to assume V is a constant at the moment. So in the most general form, I can differentiate this using the product rule, which is V dCj by dt plus Cj dV by dt equal to Rj V. And what I'm going to do here is I'm going to write this as dt. Okay, I'm going to take dt over here and write this as V dCj plus Cj dV over Rj V. And you'll see why. And if I integrate this on both sides, what I get essentially is the time, the total time is the integral of, in this case, I'm going to, what you will see here is let me just write this out. So this is going to be dCj over Rj, the first term, V cancels out, and then Cj over Rj dV over V. And any idea how I can write dV over V?
Negative d1 over v.
Not quite.
I'm sorry, d ln v.
D ln V. That's how you write it. Okay. So I can write this as dCj over Rj plus Cj over Rj d ln V. So the reason I'm writing this as time, and I'm going to call this for now BSTR2. And the reason I'm writing this is because in the context of a batch reactor, what you're typically interested in is to ask how long do your reactants need to sit in the reactor to achieve a certain level of product formation. That's the question that you would be asking. That's why I'm writing this in terms of time. That's going to be the variable of interest. And so in the special case of constant volume, until now we've been very general. So if we have constant volume, what you will notice is that d log of V, which is dV over V, is 0. dV is 0. And so in this situation, I can get my T as the integral dCj over Rj. And I'm going to call this BSTR 2.1. just to highlight the fact that it's not a general equation. I've made an assumption of constant volume. And so the way I would use these equations is to calculate, and we'll do an example, the time required for the concentration of a species to achieve a certain value beginning with Cj naught. All right. So there is another form. So we've done the molar form and the concentration form. There is a third form and the final form of these design equations that I want to introduce. And before I do that, I want to define something. And so often, when we look at chemical reactions, and I'm going to look at the general chemical reactions, there will be one of these reactant that is called the limiting reactant or reagent. And this is usually the one that gets consumed first. So often you may not have the different reactions in perfect molar ratio. You might add excess of something, let's say water, could be a reaction. But one of these reactants would be limiting, in that once that reaction gets consumed, your reaction is done, because you have no more, you need all reactions for the reaction to happen. And so without loss of generality, let A be called the limiting reactant. And you have to identify in different situations what the limiting reactant is. And so I can write my equation, my reaction, as follows. I can write it as A plus B over A, B, plus gives me C over A, C, plus D over AD. I've just divided by A, and so I'm writing this in per mole of A basis. And I'm going to define something. I'm going to define X sub A as, and this is a quantity called the conversion. And the way I'm going to define it is the moles of A reacted divided by moles of A fed. And sometimes we would just call this X, but it's typically right to define the conversion with respect to a specific reactant. And because A is the limiting reactant, can you tell me what values this conversion would take? Will it be, what would be the range? Would it be 1 always?
Anywhere from 0 to 1.
Anywhere from 0 to 1. So 0 less than X sub A less than 1. And the reason this is important is because when I design reactors, I could tell you, I want to achieve a certain conversion. I have given my reactants and design a reactor and tell me how long it's going to take for a certain conversion to happen. And we'll look at an explicit example now. So hopefully the conversion definition is clear. So the last form that I'm going to define my batch reactor design equation is going to be the conversion form. Okay, and so again, in this scenario, I'm assuming that A is my limiting reactant. And so instead of J, I'm using A, assume that one of them is the limiting reactant. And so how will I use the conversion? So I want to express the number of moles of A at time t in the reactor as a function of the number of moles of A initially, so moles of A at t equal to 0, plus or minus what? This is going to be moles of A reacted. And what will that be? So minus moles of A reacted, right?
X value.
Sorry?
The X value.
The X value, but it's not going to be X by itself because X is a fraction. If you notice here, the way I've defined X is reacted over fed, and what's fed is Na0, right? So it's going to be, somebody said conversion times Na0. So it's going to be Na0 times Xa. And so this Na is going to be Na0 times 1 minus Xa. So I have an equation for Na in terms of the conversion. So what I'm going to do is I'm going to substitute in BSTR1. And so I now have d by dt of Na, which is simply Na0, 1 minus Xa, equal to R sub A times V. And if I differentiate this and I regard Na0 to be a constant, I have Na0 minus dxa by dt equal to R sub A V. And again, I can compute the time as Na0, which is the constant, to the integral of dxa by minus RAV. And since the integral is over Xa, the limits would be typically Xa equal to 0, assuming that I'm starting with no product. That's the case, until some desired Xa star that I want to achieve conversion. And so this is what I'm going to call BSTR3, or the conversion form. And again, in the specific scenario when V is constant, I can pull V outside, and Na0 over V is simply Ca0, the initial concentration of A. So T can be Ca0, Xa to 0 to Xa star, dxa by minus RAV. And this is, I'm going to call this BSTR 3.1.
Why is the V still inside the integral? Didn't you take it outside?
Sorry?
Why is the
sorry.
V?
Got it. Yeah. All right. Okay, so let's do an example to build some intuition. So an example. So consider the gas phase reaction. And I'm going to assume that it's an ideal gas and it's isothermal, so constant temperature. And so one example is an industrial reaction that used to be quite popular, but now it's less popular because these compounds are toxic. So you have NOCl, which is a compound called nitrosyl chloride. Gives me 2 moles of nitrosyl chloride, gives me 2 moles of NO plus chlorine. And this was typically carried out at very high temperatures, 500 degrees Celsius, but doesn't matter. So I'm going to, for the purposes of this, I'm going to assume that it's gas phase, and I'm going to assume that the general form of the reaction, just to make our life simple, is 2A gives me some 3 moles of some product. And I know I should be P1 and P2, but I'm just going to assume 3 moles. It's not going to matter. Okay, let's just assume that this is our reaction. Okay, so what's the problem? The problem is that a batch stirred tank reactor is loaded with pure A at the concentration Ca0 equal to 9 moles per liter, which is dm3. And the question is, how long will it take? and again, for the batch reactor, it's the time that matters, to achieve 90% conversion for two scenarios. Scenario A is where the BSTR has constant volume. And the second scenario, the BSTR is maintained at constant pressure. So this is the question. Before we start solving, and we're going to solve this, I'd like to do a poll of which of these scenarios, A or B, do you think would take more time, or would it not matter? So I'm going to launch this poll. I'm going to do this for the first time. All right, so you have times, and you have 4 options. All right, I'm going to wait 10 more seconds. All right, 5, 4, 3, 2, and 1. All right, so let's see the results. Results are that 48% seem to think that the constant volume, BSTR, is going to take more time. And then the others think this is going to take, so this is 48%, and this is 25%. And some of you, 40% of you, which is a significant, 30% of you, significant number, think it's going to be either both of the same. And of course, some of you think it's going to be complicated. We can't answer this question. So anybody, any volunteers on people who think why constant volume will take more time?
I think constant volume would take more time because since you're releasing 3 moles of gas, you're going to have a buildup of pressure, and so a greater concentration.
And you think that would sort of hurt the reaction?
I think
I
so.
like your thinking. What about constant pressure? What do people think constant pressure would take more time? Or people who think it wouldn't matter? Anybody, any volunteers?
Maybe if you say constant pressure, then as the reaction proceeds, the volume is going to have to increase because we're producing more moles of gas. And maybe that means that our partial pressures of A are going to decrease faster than they would at constant volume, and that's going to affect our rate law.
Brilliant. I don't think I need to solve it. You've solved it. But let's see. Let's see how this works out. That's good intuition. And I want to demonstrate exactly how that will happen by looking at the equations. So Anthony is right. And let's start with, BSTR3. BSTR3. And I'm using it because I'm looking at conversion. Okay, so the time is simply NA0, and I have a conversion of starting with 0. And what's going to be my final conversion? XF?
0.9.
0.9. dx over RA or minus RA. Okay, and I haven't provided minus RA yet. So technically, it turns out you were not exactly correct because I haven't provided the rate form. And so, in other words, but for this example, what I'm going to do is I'm going to say RA is K CA squared. It's second order. Okay, and then I'm going to take K to be of the value 0.2 liters per mole per second. And so this in DSTR2, if I substitute, it's going to be K Ca squared times V. Now the first thing I can do is that V is constant. I can take V outside. And so if I take V outside, this is going to be Ca0 over 0.9 dx over K Ca squared. And actually, I'm going to also take K outside. Now I need to express Ca. So how do I do that? So I know, again, I'm going to start with the most basic equations. I know that my Na is Na0, 1 minus x. I'm just going to call this xa. I can divide by both sides by V, which is constant. And so Ca is simply Ca0, 1 minus xa. And I can substitute that. So this is Ca0 over K, 0.9 dxa over Ca0 squared, 1 minus xa whole squared. And so this, if I calculate, it's going to be Kca0, 0 to 0.9 dxa by 1 minus 1 over xa the whole squared. Now, this integral is straightforward to solve. It's essentially going to be 1 over 1 minus x, the limits 0 to 0.9. And if you substitute this, what you're going to find is that this is 5 seconds. And you can use Wolfram alpha or whatever. So that's 5 seconds for constant volume. Okay, let's do constant pressure. So in the case of constant pressure, what I have is I have a reactor and its walls can expand to keep the pressure constant. And so again, my BSTR3 is Na0, 0 to 0.9 dxa by K Ca squared V. The complication here is that I need expressions, so need expressions for Ca and V at constant pressure.
For V, since you said ideal gas law, can we just use that to substitute in for pressure instead?
So I don't have pressure in the equation at the moment, right? So I need to find V. So your idea is that I have to use the ideal gas law somewhere, right? That's your point. Okay, so that's what we're going to do. So again, for the ideal gas, thank you, Ananya. So for the ideal gas, I have P0 equal to P1, which is the initial and final or at any time. So I can say N0 RT over V0 is N1 RT over V1. And so I can remove RT because it's isothermal. And so my V1, okay, actually I'm just going to call this V. So I'm going to call this N RT over V. So my V, which is my volume, is essentially V0 N1, sorry, N over N0. That's my relationship. And so I need to calculate N. So N, right? So need to calculate N. So what is this? So N is the total number of moles. And that has to be the total number of moles of Na, the total number of moles of P. What is Na? Na0, 1 minus Xa. What is N sub P? So how many moles of XA have reacted? Na0 moles times XA, these many moles of XA of A have reacted. So for every mole,
is it 3/2 times
correct.
Na0 times XA?
Absolutely. So 2 moles of XA reacting produces 3 moles of P. So this has to be 3/2 moles of Na0 XA. Now, chapter 4 of Fogler does this in a very, very formal way. You know, it involves general equation, but I almost don't remember that. And once you're given a stoichiometry, it's the only question of writing these balances. Hopefully this is clear to everybody. Any questions?
Yeah, I have a question. Can we always just take the stoichiometric coefficients for the products the way you did, where we added all the different products and said they were all 1p?
Not always, especially if you have a reverse reaction. In this case, you don't have a reverse reaction, so we don't care. So if you have a reverse reaction, you might have to be a little bit more careful. Okay?
Yeah, thank you.
So I can add this up, and what I'm going to get here is, this is going to be Na0, 1 plus XA/2. And so the number of moles is increasing with time because 2 moles are getting consumed to form 3 moles. And so now if I substitute this into V, what I get is V is V0, 1 plus XA/2. So again, if you rely on your intuition, what should have been obvious is that for an ideal gas, this reactor has to expand in volume. So I can, now I'm done. Actually, I'm not done because I need to compute Ca, which is Na/V, but I have everything. I have Na0, 1 minus XA over V0, 1 plus XA/2. And this is Ca0, 1 minus XA divided by 1 plus XA/2. And so I'm ready now to compute my integral. So what you will see is that this is Na0 over K from 0 to 0.9 dxa times Ca0 squared 1 minus x by 1 plus XA/2 the whole squared times V0 1 plus XA/2. And so I can ultimately substitute and do some algebra and write this as 1 over K Ca0 integral 0 to 0.9 1 plus XA/2 divided by 1 minus XA the whole squared dxa. And if you substitute, you can write this as 1 over K Ca0, and I'm going to just split the integral up and you will see why. And so the first integral is going to be 1 over 1 minus XA the whole squared dxa from 0 to 0.9 plus 1 over 2 K Ca0 0 to 0.9 XA dxa by 1 minus XA the whole square. So what you have obtained effectively is that T at constant pressure is T at constant volume, which is this first expression, plus something. And the something is positive. You will notice if you solve it on Wolfram alpha. And it turns out that if you now substitute this is 5 seconds, and this comes out to be, I think, something like 2.1 seconds. So you have 7.1 seconds in the case of constant pressure. So essentially, T constant pressure is greater than T constant volume. And again, I want to just emphasize physically why this is happening. It's because you have a second order reaction. And so what's happening is that as you produce more and more product, the number of moles is increasing. And so if you have to maintain constant pressure, the volume has to increase. And if the volume increases, the same reactants will have a lower concentration. And so they take more time to find each other. That's the reason why you have more time is increasing to achieve a certain conversion. Now the corollary is, and this is something for you to figure out in the homeworks, is what happens when the reaction rate law is first order. So just before we close, any thoughts? Would you get the same answer? Would you see something different? It'll be the same for both. Anybody wants to say why it would be the same for both? Well, moles are not constant. Moles are still changing.
You're still creating more moles than you're using. So in order to maintain a constant pressure and temperature, the volume still has to increase, and that still decreases the concentration. It's just going to be like less of a dramatic difference because it's first order as opposed to second, but it'll still take longer at a constant pressure.
Right. I would argue that it actually will not matter. And you should check. I mean, I could be wrong. The reason is you have a first order equation, which means that these two molecules don't need to find each other. As long as those molecules are there somewhere, and as long as you're maintaining constant temperature, you will still proceed, and you will see. So I encourage you to mathematically try and solve and prove to me or disprove to me that you will not have the same time. And my guess is, I haven't done this, I was just doing this a couple of hours ago, is that you will find the same time. It won't matter.
Does that assume that it's an elementary reaction and not like?
Correct. So it assumes it's an elementary reaction, right? So I've provided you the rate law. So what I would sort of mention, Elizabeth, is you just want to try and do the same analysis for when your RA is essentially KCA. And my simple argument here is that essentially you will have only one power of 1 over XA over 2, and that will cancel 1 over XA over 2. Exactly. So you won't have this additional term. That's the reason.
Okay, I see.
But feel free to convince me that I'm wrong. That's fine.
No, I believe you.
I don't believe myself, so go home and do it.
Another place to look would be for the moles expression. If you look at that, and if you look at adding the moles of Na plus the moles of product, if it's 1-to-1, you'll see that you get N equals Na naught because the number of moles isn't changing.
The number of moles isn't changing for, okay, so I just want to say the class is done. Those of you who want to leave, please leave, but I want to continue this discussion. So you're saying, Ananya, that the number of moles won't change? I feel like this equation over here will still hold true, because the rate law R sub A has not been invoked. This is purely stoichiometry. So this is purely stoichiometry. So the number of moles will still be increasing. You will still see expansion of volume. It just won't matter for the reaction because the reaction is first order in this scenario.
Okay.
Any other questions?
If, say, we had a different reaction where the number of moles was conserved, it wouldn't make a difference no matter what the order of the rate law is, right? Because your moles are constant.
Yes.
Okay.
And I think you should just try and figure it out for yourself, if that's the case. So can I scroll up to the work for constant volume? Absolutely can.
So Professor, I have a question. I'm a little bit lost. So what was our final consensus about what happens when the reaction is first order?
When the reaction is first order, T constant P equal to T constant V. The time is going to be.
All right, thank you.
And again, please check this and let me know.
If the reaction is below first order, does T constant V take longer?
It's an interesting point. I don't know. I think it would take longer. Maybe try it. Do you want to volunteer yourself to give us an answer on Piazza?
Sure, I can give it a shot and see how long it takes me.
All right, thank you. By the way, these integrals, if none of you have used Wolfram Alpha, it's pretty easy to just go up and solve. I mean, I still do them by hand, but you can solve them on Wolfram Alpha. And so